Mechanical properties of materials are associated with the ability of the material to resist mechanical forces and load. These properties indicate how the material responds under specific stress, which helps to determine its suitability for different applications. In material science and engineering, the mechanical properties of materials are fundamentally important because every mechanical property has specific applications in designing components in the manufacturing industry, automobile, forging, power plants, aerospace, etc. Therefore, as an engineering student or engineer, it's important to understand and differentiate the various mechanical properties of materials used in engineering. Knowing this information helps you select the appropriate materials for your designs and engineering applications. Welcome to James Sword Research Channel. In this video, an overview of the common mechanical properties of engineering is discussed. Endeavor to watch the video till the end for better understanding. If you find the video helpful, please like and share the video, subscribe to the channel, and also turn on the notification icon for more content. 1. Strength. In the mechanics of material, the strength of the material refers to the ability of the material to resist an externally applied force without breaking or yielding. That is the ability of a material to withstand an applied load without failure. The strength of a material is evaluated based on the amount of load it can take before fracturing. There are different types of material strength. They are compressive strength, tensile strength, shear strength, fatigue strength, torsional strength, bending or flexural strength, etc. 2. Elasticity. Elasticity is the ability of a deformed or stretched material body to return to its original shape and size, after being stretched out or altered by a force. When a material is deformed due to an applied force, it undergoes internal changes that cause stress. If this force is removed, and the material returns to its original state, it is said to exhibit elasticity. Materials that display a high degree of elasticity are termed elastic materials. To a lesser or greater extent, most solid materials exhibit elastic behavior, but there is a limit to the magnitude of the force and the accompanying deformation with which elastic recovery is possible for any given material. This limit is called the elastic limit. The causes of elasticity vary depending on the type of material. Polymers including rubber may exhibit elasticity as polymer chains are stretched, and then subsequently return to their original form when the force is removed. Metals may display elasticity as atomic lattice changes shape and size, again returning to their original form once the energy is removed. Elasticity behavior has tremendous implications in engineering design, especially in structures that must regularly experience and recover from stress. Elasticity is determined by the stress-strain curve, which essentially displays how a material responds to stress. 3. Plasticity. Plasticity is the ability of a solid material to undergo permanent deformation, which is a non-reversible change in the shape of the object in response to an external force applied to it. Plasticity is observed in most materials, particularly in metals, soils, rocks, concrete, and foams. However, the physical mechanism that causes plasticity can vary widely. Plasticity in metals is usually a result of dislocations. 4. Ductility. Ductility is a mechanical property that describes the ability of a material to be stretched, pulled, or drawn into a thin wire and sustain plastic deformation without failure. It is a measure of how much a material can be deformed or elongated under stress before it fractures. Ductility is an important consideration in engineering and manufacturing, defining a material suitable for certain manufacture and capacity to absorb mechanical overload. Ductility may be expressed as % elongation from a tensile test. A material that is said to have high ductility is called ductile material, and it is associated mainly with metals such as gold, platinum, silver, iron, copper, etc. All of these can be stretched into fine wires and used for either jewelry or electrical wires. 5. Brittleness. Brittleness refers to the property of a material that allows it to fracture or break abruptly under stress, without significant prior deformation. It is the breaking of a material with little permanent distortion. Brittle materials such as glass, ceramics, bricks, cast iron, etc. when subjected to tensile loads, snaps off without giving any sensible elongation. This lack of deformation before failure is what defines brittleness. Brittle materials tend to have high hardness and low toughness, meaning they can withstand high compressive stress but are susceptible to cracking and breaking under tensile stress. 6. Malleability. Malleability is the ability of a material to be rolled, flattened, or hammered into a thin sheet without cracking or breaking. It is the ability of a metal or metal alloy to be formed into a variety of shapes. Malleable materials can be reshaped into new forms without losing their internal structure or strength. Malleability varies from one metal to another. It is a critical property for metal fabrication, where metals like steel and aluminum can easily be formed into different shapes for use in different industries. Factors that can affect the malleability of metals and alloys are the strength of the metallic bond and the temperature of the metal. 7. Toughness. In material science and metallurgy, toughness is defined as the amount of energy that a unit volume of a material can absorb after being stressed up to failure. Toughness can also be understood as a measure of a material resistance to crack propagation and failure. The key to toughness is a good combination of strength and ductility. In essence, it's the total area under the stress-strain curve, including the stages of both elastic and plastic deformation. Two major types of toughness include fracture toughness and impact toughness. Fracture toughness is a measure of the quantity of force necessary to propagate a pre-existing fault. Impact toughness is the ability of a material to absorb energy before fracture. The Charpy and IZOD notched impact strength tests are typical ASTM tests used to determine toughness. Toughness is calculated in terms of energy absorbed per unit volume. It is mathematically expressed as toughness equal to the total energy absorbed till fracture, divided by the volume of the material. The SI unit is joules per cubic meter. 8. Creep. When a part is subjected to constant stress at high temperature for a long period, it will undergo a slow and permanent deformation called creep. Creep deformation is time and temperature dependent, and can occur in metals and polymers at elevated temperatures and constant stress. Creep is usually of concern to engineers and metallurgists when evaluating components that operate under high stresses or high temperatures. Unlike brittle fracture, creep deformation does not occur suddenly upon the application of stress. These deformations are typically in the form of dislocations, where voids are formed either on the grain boundaries or within the crystal structure of the grain due to the applied stress. These voids or dislocations then travel throughout the material over the lifetime of the part, resulting in permanent deformation. Creep occurs in three stages, namely primary, secondary, and tertiary creep. The primary creep starts at a rapid rate and slows with time. The secondary creep has a relatively uniform rate, while the tertiary creep accelerates and terminates when the material breaks or ruptures. 9. Hardness. In material science, hardness is the ability of a material to withstand localized plastic deformation, such as indentation over an area, or a scratch induced mechanically either by pressing or abrasion. The three types of hardness are scratch, indentation, and rebound hardness. Scratch hardness measures how resistant a material is to permanent plastic deformation due to friction from a sharp object. The most common test for this type of hardness is the Mohs scale, which is used in mineralogy. Indentation hardness measures the ability to withstand localized plastic deformation, that is, surface indentation. It also refers to the resistance to permanent deformation when subjecting a material to a continuous load. Common indentation hardness tests are the Rockwell hardness test, Vickers hardness test, and Brinell hardness test. Rebound hardness, also known as dynamic hardness, measures the height of the bounce of a diamond-tipped hammer dropped from a fixed height onto a material. The device used to take the measurement is known as a scleroscope. 10. Machinability. Machinability defines the ease at which a material, mainly metals, can be cut, shaped, or finished with any machining process. A material is more machinable when cut with normal cutting speed and minimal power without deforming the cutting zone. A material has poor machinability when it requires more effort and high cutting forces, which results in more deformation. The machinability of a material depends on its physical and mechanical properties, as well as its condition.